Hello, my name is Lee Presser. This is my show. I speak frequently to very interesting people. Some of these conversations are so exciting, so intellectually stimulating, I thought others might like to listen in. This is the reason we started recording Conversation with Lee Presser. Welcome to Conversation with Lee Presser. The high temperature last year, on July 4th, 2012, in St. Louis, Missouri, was 105 degrees Fahrenheit. That was a record high. It was the 8th day of over 100 degree temperatures in St. Louis. That night, the other July 4th record was set for the highest low. It cooled off overnight to only 83 degrees. This year, the July 4th high was 84 and the low was 59. Now, how does that happen? Mark Twain is quoted as saying, "Everybody talks about the weather, but nobody does anything about it." Our guest today, Dr. Charles Graves, observes it and makes predictions as to its future behavior. He's an associate professor in the St. Louis University Department of Earth and Atmospheric Sciences. Dr. Graves began studying global-scale precipitation in 1992. During the last decade, he's been working with the National Weather Service forecast offices forecasting problems created by high-impact weather, including heavy rainfall, snowfall, and severe weather. Today, he and I will be talking about the weather. Dr. Charles Graves, welcome to Conversation.
Thank you. It's a pleasure to be here.
So, a lot of people say of weathermen, boy, I'd love to have that job. 50-50, throw the dice, you could be right, could be wrong, still get paid. What is meteorology really? What is it that you and your colleagues are actually doing?
Meteorology is the study of the atmosphere and everything that affects it and how it will evolve over time. So we're looking at not just is it going to rain or will it be sunny, but we're also looking at how the sun might impact today's weather because of the time of year it is, or maybe because of cloud cover. I have colleagues that study the aerosols, the small little particles that float around in the atmosphere, and how that affects things like the formation of precipitation. Mm-hmm. So anything that's going to impact the weather, they typically are studying. We are very lucky in that most meteorologists, their laboratory is right outside. So they go out and observe the weather, and that's one of our major tools that we use for analyzing and understanding what happens.
Did I read when you were young, you set up your own little weather station?
Yes, when I was in 3rd grade, I liked to build things, and I came across a plan to build a weather station. And so for my science project in 3rd grade, I built a weather station, and then I decided if I'm going to build a weather station, I probably should take some measurements, and I kind of got hooked.
What's in a weather station for a 3rd grader?
Well, I built something that acted like a barometer to measure air pressure. I had a wind vane. I had an anemometer that measured wind speed. I had a glass there to measure rainfall. I had a mirror that I could use to look at the reflection of the clouds to track the direction that the clouds were moving. So mm-hmm. that was...
Up until, well, first let me ask you, you mentioned that you had this thing to measure air pressure.
Yes.
Why don't we discuss, really simple things like, what's a high? What's a low?
The atmosphere has lots of sizes of phenomena. When we typically talk about a high pressure system or a low pressure system, we're usually talking about a relatively large feature in the atmosphere. It's probably on the order of 300 to 500 miles in size. And
you're talking about across?
Across, yes.
Not up.
Not up. And it represents effectively the weight of the column of air that's above that point. Mm-hmm. So low pressure systems often are associated with with light air, which would be warm, typically also humid. So low pressure tends to be associated with warm air and moist air, mm-hmm. which is also the good ingredients for things like thunderstorms. Mm-hmm. High pressures normally are associated with cold air and dry air. So high pressures tend to be colder and drier. There are exceptions to those rules, but that generally is a characteristics of the atmosphere.
Now it's interesting you mentioned that lows have water vapor, more water vapor in them. You think of water as being heavier than air, so you would think that,
Yeah.
you know, that if the low has more water, it should be heavier, but it's not.
Right.
Now, are there mountains and valleys? I mean, is a low pressure like this and a high pressure like with a hump on it, or is it all just flat?
Well, when we look at high pressure and low pressure systems on a weather map, that tends to be what we see. A low pressure system tends to look like a trough or a dip, okay? And a high pressure tends to look like a ridge or a hump. When you look at them horizontally, that's the pattern you see. When you look at them vertically, it turns out that the atmosphere is three-dimensional. So what happens is the lowest pressure you see at the surface tends to shift to the west with height. So as I'm looking at the surface and I see the low pressure over St. Louis, if I go up to the level of the jet stream, that lowest pressure is now shifted back to maybe Kansas City or in western Kansas. And so there's a three-dimensional structure of that system that actually is critical for its evolution.
Mm-hmm. And when there is a high pressure and you've got this hump you're talking about, does air pour off of it into the low, and this is what causes like these winds that we see when there's going to, like today's July the 9th.
Right.
Okay. And tomorrow is there's supposed to be a front change.
Right.
Okay. And so there's probably going to be wind with it, right?
Yes.
Why?
The initial instigator of the wind is exactly what you described. You have high pressure in one area, you have low pressure in another. If you think about it, the air is going to want to flow from high pressure to low pressure. Okay? If the Earth wasn't rotating, that would be the story. But now that the Earth is rotating, the air gets deflected because of that rotation. And in the northern hemisphere, that deflection is to the right. So as the air starts to move from high pressure to low pressure, then it gets diverted to the right. And so that's how you start to develop the circulations that you see around a low pressure system and a high pressure system. Recently, in the St. Louis area, we've had this low that has sort of been meandering around. I hear this, the TV weather guys talk about this low that's meandering. What do they mean by there's a low and it's meandering around? In a normal situation, you have a low pressure system that tends to be tied with the jet stream. And so the jet stream tends to steer it along as it moves.
Why don't you describe what is the jet stream?
The jet stream is a region about 5 to 7 kilometers, 5 to 7 kilometers, it should be about 6 miles above the Earth's surface. We have very strong winds. It's really formed because we have cold air to the north as you move toward the poles, and you have warm air to the south. And instead of just being purely east-west, it gets waves in it and oscillates.
North and south.
North and south.
Right.
And so it tends to direct these low pressure systems and move them from west to east, which is what we experience on a daily basis. Well, this low pressure system decided to separate itself from the jet stream, which is up in the border between Canada and the US, and so it separated itself, so there's nothing to steer it around. So it just kind of sits and spins. Mm-hmm. And without a flow to direct it around, it just kind of meanders.
And so it's spinning counterclockwise?
Yes, counterclockwise.
Counterclockwise. And normally in St. Louis, weather moves from the west to the east. Is that pretty much the whole United States?
Yes.
From the west to the east?
Yes.
But now we have seen lows and recently a high. Right now, as a matter of fact, there is a high, which is just to our west, but it's moving further west.
Yes. And so occasionally when you get these, this is more typical in the summer than in the winter, you get these systems that get separated from the jet stream, and so they don't have that steering mechanism, so they kind of float around. Occasionally they would call what we call retrograde, which was move from east to west. That's what this high is doing. It's not unheard of, but it is somewhat rare. Mm-hmm. And it tends to make the type of weather that we've been experiencing.
Mm-hmm. Now, as I mentioned in the introduction, a year ago, July 4th, the whole summer was
yeah.
ungodly hot. And then all of a sudden, now this year, it's been really kind of nice. I mean, we've had a few hot days, but it's been kind of nice. How does that happen? I mean, how is it that one year can be so dramatically different from and I don't remember what year it was, but a few years ago, it was, some people called it the summer that didn't happen.
Yes, yeah. It's, if I knew the answer to that,
you'd be head of the National Weather Service.
Yeah, it's a combination of many factors, and by factors, by many, I don't mean 10 or 20, I mean thousands, because you have things like the winter snow cover that develops over the Canadian and how far south that progresses. Mm-hmm. You have the current status of the El Nino or the La Nina system that has an impact. There are other climate indicators or features. One of them is called the Pacific North American Oscillation that tends to impact how the jet stream meanders. Remember we talked about the waves, the north-south waves. Well, those climate factors tend to want to influence the jet stream into certain patterns. And as those climate oscillations or features, phenomena change with time, then you tend to change from years that are exceptionally warm to years that are exceptionally cool.
And now are we taking and moving the exceptionally warm laterally across the United States? For example, on July 4th, out in the west, not all the way to California, but starting maybe at the California border and working back through the Rocky Mountain states, it was unusually hot.
Yeah.
So are we saying that last year it was here and this year it's been moved back, or is that like an entirely different phenomena?
That's a loaded question, actually, a very good one. The simple answer is typically yes. What happens is, we talked about that jet stream, and very often if we have a dip in the jet stream in the eastern part of the United States, that means we have a ridge or a hump in the western part. So the western part tends to be warm, the eastern part tends to be cold, okay? And the atmosphere likes to be in that kind of configuration, or maybe the reverse. So the East Coast or the eastern half of the United States, the western half of the United States tends to be oscillatory in nature. Not always, but it tends to be that way. So these climate factors can shift that pattern to the east or to the west a little bit, and that's the way they like to encourage the atmosphere to behave. Since we're kind of talking about a connection between weather and climate, what I'd like to do is give you an analogy that I give my students to get people to think about it in the right way. So you remember growing up, you're sitting at the dinner table, and you take your glass of milk and you move it to the edge of the table. Mm-hmm. First thing mom does is she yells at you. She says, don't put it there, the milk's gonna get spilled. Well, of course, you don't listen to her. And then your bratty little sister, sure enough, knocks the glass over. And mom yells at you and you get in trouble. And so what I ask my students is I say, okay, did moving that glass of milk to the edge of the table cause the milk to be spilled? Well, not directly. What really caused the milk to be spilled is your sister hitting the glass. What happened is moving the glass to the edge of the table made it more likely to occur. That's what climate does to weather. It doesn't directly cause things, but it makes them more likely to occur.
Now, define the difference then between climate and weather then. So that seems pretty interesting.
So then climate is more long-term tendencies. So climate would be, a climate forecast, for example, would be say that in January it's going to be colder than it is in July. Okay, not a real difficult forecast, but okay. I'm not telling you exactly what the weather is going to be like in January, but I'm telling you something about the general characteristics. So typically we envision climate as the average conditions that you encounter at a given location, typically at a given time. Weather, on the other hand, is much more precise. It's like it's going to rain at this time at this location.
Okay. You've mentioned the word climate, and so we're going to take off into political territory. Suddenly, meteorology has become political, as so many things in America has been, but it's become very political. And in some cases, I have observed that if a meteorologist says something that the press disagrees with, suddenly this meteorologist is castigated or made fun of in other ways, or in some cases even let go from their jobs. What's that all about?
That's actually a somewhat frustrating aspect of meteorology, and I think science in general. Science in general is built off of being critical and skeptical, okay? You put forth a hypothesis, and then you test that hypothesis. And then another scientist says, well, he said this, that should imply X, Y, and Z. I'm going to go and test X, Y, and Z. And he's going to say, oh, look, X, Y, and Z didn't work. Either your hypothesis is wrong, or we've got to reconfigure things. I mean, that's been the way of science
since the 1400s.
Yeah. So we're developing our understanding by a critical analysis of what's going on and challenging views. So the general public often views that as disagreement when it's really just the natural state of evolution of the science. Somebody puts forth an idea and then it gets challenged. It's not and so that's how you build confidence and consistency in understanding what's going on.
Mm-hmm. In today's, and again today being July the 9th, USA Today, there's an article, and it says, more hurricanes on horizon. And as you get into the article, it says, one of the biggest debates in the climate change research community in recent years has been whether global warming will make hurricanes stronger, more frequent, or longer. Then over here we have a Georgia Tech climatologist, Judith Curry, who is not part of the study, that says the conclusions come with substantial uncertainties. They rely on a large number of assumptions that have limited support. Okay. Now, the press would have the public believe that this is all settled, that somehow human beings, through their human activity, have had a major impact on climate. Is that settled?
Depends on how you ask the question.
Okay.
Okay? Because if we go back to my analogy again with the glass of milk, the equivalent question is changing climate. Does that shift the glass of milk from the center of the table to the edge of the table? Okay? And the only way we know how to determine that is by looking at things like how often does the milk get spilled? Mm-hmm. Well, but there are lots of features that can drive, I mean, let's take a bizarre example of that case. The milk could be spilled because there was an earthquake, mm-hmm. Okay? It had nothing to do with global change. So you have this difficulty of assessing what's going on by looking at events that occur. The way the article and the way the scientists try to approach that is, well, if I look at how frequently the milk gets spilled, okay, at some frequency, it's more likely that the glass of milk got moved to the edge of the table because it keeps happening more often than what you would expect if it was in the middle of the table. And that provides the evidence that says something's changed.
Okay.
Okay? So that's the way they're trying to tackle the problem.
Something has changed. Now, as a young person, many, many years ago, I was taught that the sun is the primary driver of weather on planet Earth. Okay? And here's a question for you. When did the last ice age begin?
Well, there was a little ice age that goes back to...
Well, yeah, not that one. I'm talking about the one that scraped eventually all the way down just north of here.
Oh, you're asking me to remember. I'm trying to remember.
Is this like about 100,000 years ago?
Yes.
And then it ended something like 10 or 15,000 years
right.
ago. So there really was like an 85,000 year period
Yes.
where the weather was kind of cold
Yes.
on planet Earth.
Right.
I'm just wondering how we can tell in a short span of time from, say, the end of World War II, or even from the end of the 19th century to today, what weather is doing in the long term.
Yeah, that's a very difficult question because climate has many timescales associated with it. If you start looking at the 100,000 year timescale, then there are processes that you have to describe and understand and quantify.
Well, like the wobbling of the Earth at
right.
the pole. Yeah,
right.
Remember
Those
that?
sorts of the wobbling of the Earth. It turns out that the path of the Earth around the sun goes from something more circular to more elliptical. Okay, those changes then impact how much energy comes from the sun. And then that has an impact on climate. If you look purely at the total change in incoming solar radiation from those things, it doesn't look like it's enough to cause the type of climate changes that we've seen in the past.
Ah, okay.
Okay?
That's
so
a
what
good
happens
point.
is it must be coupled with something else.
Okay.
Okay? Historically, what the scientists have seen is there are mechanisms that change things like the amount of carbon dioxide in the atmosphere, and there tends to be a very close coupling on the large time scale, when you're talking about 100,000 years or more type time scale, between temperature and the amount of carbon dioxide in the atmosphere. So there tends to be what we call a feedback effect. That is, and I can give you a really good simple example of that. You can imagine if we drop the amount of incoming solar radiation from the Earth, from the sun to the Earth, just a little bit, maybe that's enough to cause a little bit more snow over the winter. So you get more snow. Well, now what happens is that snow is white and bright and it reflects solar radiation. Mm-hmm. So now we have less solar radiation being absorbed, warming the Earth, more of it gets, so then the Earth cools a little bit more. Yeah, it becomes a repeating cycle. And so these type of feedback effects are the things that coupled with the changes in things like solar radiation drive the climate system on those long scales and become very fascinating. I just dabble a little bit in this area, but they're very fascinating. And the hard part is you don't have any real good direct evidence. You have to work very hard at getting evidence for changes in carbon dioxide, et cetera, from ice cores, from other indirect measurements. It's a very fascinating field.
Very interesting. Now, I would have to say that it seems warmer to me over my lifetime than it used to be when I was younger. And storms in the St. Louis area, or precipitation in the St. Louis area, seems different than it did, say, back in the 1970s. Am I mistaken as to the precipitation, or is that just because, it's so long ago and my memory's failing me?
The evidence suggests that there are changes in precipitation. In fact, back in the 70s, there was a field program in St. Louis called METROMEX that studied how a urban environment impacts the precipitation patterns. Mm-hmm. And what they found is there's an enhancement of precipitation downstream that is on the other side of the river, since most of our weather goes west to east on the other side of the river, because of the city. The added aerosols that get put into the atmosphere are likely playing a role at enhancing the development of precipitation, almost like cloud seeding. And so urban environments do have an effect on the precipitation field. Now, more recently, it's a more difficult question to answer because we haven't done a field program like METROMEX. I mean, that was, we won't count how long ago that was.
Yes, I know. It was like, that was after so many years ago.
Yeah. I was a little younger.
Yeah, me too. Okay, well then let me ask and move on. By the
Yeah.
way, we're now like about 4 minutes left here, so we're coming to the end. If there's anything you want to say, make sure you get into it. A couple years ago, the airport got hit by a tornado, and there was severe damage across what would be considered the northern corridor of St. Louis. St. Louis County and St. Louis City, or not even the city, it was just North County, and then skipped across into Illinois. This year, we had another event which seemed to follow the very same pattern. And it got me to thinking, why? Or ask the question, you know, why does, I mean, is there some steering current or something that would take a similar storm like that?
Well, it turns out that that seems really interesting type of argument you want to make, but it turns out that the two types of storm dynamics that were involved were very different. So it's not as if the atmosphere has now found a preferred formula for creating these storms. Because
and yet rainstorms oftentimes will come, and I've seen this happen, they come and then all of a sudden they make this what they call the right turn.
Yes.
Now, is that a pattern or
yes, that's a pattern. Very often what we find is thunderstorms, their fuel is moisture. Okay? And so in the central part of the US, the best source of moisture is typically to the south. So the storms start off moving west to east, but then they find environments more conducive for them further to the south, so they take a nose to the south, so they make that right turn. And that's actually a unique aspect of the central part of the U.S.
Does that have something to do with the land, the trees, the river, or I mean, what?
Well, it probably involves the Gulf of Mexico, because we have, that's our source of moisture.
Right,
okay?
But it's going the other way. It's going towards the Gulf.
Right, because that's where the moisture is coming from. So it's heading
towards the source.
Right, it's heading toward the source. And that flow from the Gulf of Mexico toward the central part of the U.S., that preferred flow appears to be tied to the change in elevation as you go west. As you go west toward the mountains, the elevation is higher, and so that tends to create what we call southerly flow and a low-level jet, which is feeding those systems.
Yeah. Well.
Yeah.
This is very interesting. I want to say, first of all, we're out of time, and it's gone by way too fast. We're going to have you back and ask a whole bunch more questions and get more educated here about the weather. It's been fun. I really enjoyed having you today.
It's been a pleasure. Always fun talking about the weather.
Well, that's what people do. Well, thank you very much for coming and being with us today.
Okay, you're welcome. It's my pleasure.
And to my audience, I've been speaking with Dr. Charles Graves. He is an associate professor of meteorology at St. Louis University in the, what is it, Earth and
Atmospheric Sciences.
Earth and Atmospheric Sciences Department at St. Louis University. As a matter of fact, they have some really good people that come out of that department. We're going to be uploading this to YouTube, so if you want other people to see it, go to YouTube. Thanks. See you next time.